Hello and welcome to today's video, which is about the gamma function. And this, in my opinion, is one of the coolest functions in math, at least one of the coolest that I know about. And today I'm going to be talking about one particular form the gamma function will take, which is an infinite product formula, originally discovered by Euler. So in today's video, here's the plan of what we're going to do. We're going to start by exhibiting Euler's infinite product formula, or definition rather, of the factorial function, which is pretty similar to the gamma function, as we'll see. We'll then apply that formula to non-integer values. Specifically, we're going to apply that formula to n equals 1/2. And when we do that, we're going to compute, in effect, 1/2 factorial. So we're going to find the factorial of a non-integer number, which is very cool. We're then going to check some properties of this new function, make sure that it has the desired properties one would expect from a factorial function. So check that our new function has the desired properties. And in so doing, we'll also show why 0 factorial is defined as being equal to 1. And then I'm going to introduce the gamma function, which is the main point of today's video. Again, this will be the infinite product form of the gamma function. So Euler developed this formula with a specific goal, which was to express the factorial of a number, which we can call n, as an infinite product. And in so doing, we can stretch the definition of the factorial to include non-integer inputs in the formula. But first recall, n factorial, if you remember from high school algebra or probability, is equal to n times n minus 1 times n minus 2. You basically reduce the value of the integer every time, multiplying all the way down to 1 for n a positive integer. Right, so this definition only works if we're starting out with a positive integer. For example, 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 factorial would be 4 times 3 times 2 times 1. That's how the factorial was originally conceptualized. And so what we can do is we can actually graph the factorial of these different positive integers on our xy coordinate system. I'll make a little chart over here with n and n factorial. So 1, if n equals 1, n factorial is 1, so I'm going to graph 1, 1 there. 2 factorial equals 2. I'll put that down there. And then 3 factorial will equal 6. You can see this actually increases very rapidly. And then 4 factorial equals 24. That's going to be somewhere up there. And so then the natural question emerges, is there some line we could draw representing a function that would interpolate at all these intermediate values? In other words, there's an infinite number of ways of connecting these dots. We would want our interpolating function to include the idea that 0 factorial equals 1. I'm going to prove that. And it might also define the factorial for negative numbers as well. We don't know yet what this graph should look like. This is just a guess. In fact, this guess is going to be shown to be wrong. But the question remains, is there a more general function that extends the factorial beyond integer inputs, beyond the positive integers? That's what we're looking to do here. We're going to see that the answer is yes. Leonhard Euler discovered the following formula. He found that if you take an infinite product starting with 2 over 1 raised to the power of n, multiplied by 1 over 1 plus n, close brackets, that's the first term in the product, now open brackets again, times 3 over 2, to the n times 2 over 2 plus n, close brackets, open brackets, times, I hope you're seeing the pattern here now, 4 over 3 to the n times 3 over 3 plus n. And this is an infinite product, so this is going to go on for an infinite number of terms, but we're going to take the limit at infinity. So we'll get to the last term in our series, which we'll call the mth term, and this will be m plus 1 over m. Notice that the numerator is always 1 more than the denominator, all to the nth power, times m, this is our mth term, over m plus n. And this is an infinite product, so it equals n factorial when we take the limit as m goes to infinity, as we multiply out infinitely many of these terms. So this infinite product formula is very appealing because remember that the factorial was originally conceptualized as a product, but now we see it as the limiting case of an infinite process. And if we plug in a positive integer for n, we recover the factorial value as we originally defined it. So let's see how this works in practice. We'll do an example. We'll let n equal 5. So when we plug 5 in for n, we should get that 5 factorial equals 2 over 1 to the power of 5 times 1 over 5 plus 1. Remember, we're subbing in 5 for n here in the formula, times 3 over 2 to the 5th power times 2 over 5 plus 1, 5 plus 2, excuse me, times 4 over 3 to the 5th power times 3 over 5 plus 3, and so on. We're going to multiply this out all the way to the mth term, so we're going to get, again, m plus 1 over m to the power of 5 times m over 5 plus m. And we're going to take the limit of this expression as m goes to infinity. So let's see, does this equal 5 factorial? Well, we'll do some simplification here. I'm going to cancel out the 2's there. The 3's cancel out. That 4 in the numerator and that term will cancel a 4 in the denominator of a term that I haven't written out. And then there's going to be an m in the numerator and m to the 5th rather, canceling out the m to the 5th in that denominator. When you do all those cancellations, that m plus 1 term is the only term to survive cancellation apart from 1 times 2 times 3 all the way up to m, those terms that I wrote in blue. So I'm going to write those out there, 1 times 2 times 3, dot, 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 times m, times m plus 1 to the 5th, which I'm putting in purple, and that will all be over 5 plus 1 times 5 plus 2 times 5 plus 3, and so on, all the way up to 5 plus m. And now I'm going to make the following simplification. Note that in the numerator, what I have there is actually the 1 times 2 times 3, dot, 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 all the way up to m. That's actually m factorial. So I'm going to rewrite m factorial as m times m minus 1 times m minus 2, dot, 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 all the way down times 8, 7, 6, times 5, times 4, times 3, times 2, times 1. And remember that m is becoming a huge number. We're taking the limit as m goes to infinity, all times m plus 1 to the 5th. And I'm going to do something clever in the denominator also. First of all, I'm going to add 5 and 1, so I'm going to get 6, then 7, then 8. I'm just simplifying those terms. But then, I didn't write them here, but I'm going to write the next few terms also in terms of m. Eventually I'm going to get to a number which is 2 less than m. I'll write that as m minus 2, then m minus 1, and then m will be in that product. And this thing goes all the way up to m plus 5, or 5 plus m. So that's my denominator. I hope that's pretty transparent what I'm doing there. Because now I can do these cancellations. I'm going to cancel 6, 7, and 8. I'm going to cancel m minus 2, m minus 1, and m. And look what we're left with. We're left with 5 times 4 times 3 times 2 times 1, which is, of course, 5 factorial. And the only other terms that are left in this expression are m plus 1 to the 5th, which I'll write out as m plus 1 times itself 5 times. And that's going to be over m plus 1 times m plus 2, and so on all the way up to m plus 5. And now, when we take the limit in this expression as m approaches infinity, the ratio in that fraction goes to 1. So we are left with 5 factorial, and the formula works. I want to point out one more thing. I'm just going to rewrite that last line from the calculation we just did. This thing equals 5 factorial. We can deduce something in general, which is that if I plug back in n place of 5, then we would say n factorial equals, again, we're taking the limit as m approaches infinity. I'm highlighting in yellow what that was. Again, that was m factorial. So in general, n factorial equals the limit as m approaches infinity, m factorial times m plus 1 to the n, all over what? In the denominator, again, those terms were 5 plus 1, 5 plus 2. I'm now subbing back in n, so I'm going to get n plus 1 times n plus 2. And that last term in the product for the denominator was m plus 5. Subbing in n back for 5, the last term will be n plus m. So this is a neater way of writing the infinite product definition for the factorial. I'm just going to put a box around it. And again, the power and the beauty of this formula is that it's general. We've shown this works for positive integer inputs, recovering the factorial as we originally understood it, but this is a general factorial function. So let's see how this works. So now let's apply Euler's infinite product formula for a non-integer input. We're going to let n in the formula equal 1/2. And Euler himself did this, so we're following in his footsteps. So let n equal 1/2. Then, by Euler's infinite product definition, 1/2 factorial should be equal to, here we go again, 2 over 1 to the 1/2 power times 1 over 1/2 plus 1. Close brackets, open brackets, times 3 over 2 to the 1/2 power times 2 over 1/2 plus 2. Close brackets again, open brackets, times 4 over 3 to the 1/2 power times 3 over 1/2 plus 3, close brackets, and so on until we get to our nth term. And now we have to recall, what does it mean to raise something to the 1/2 power? Well, remember, x to the 1/2 power is defined to be equal to the square root of x. So I'm going to rewrite this. 1/2 factorial equals, open brackets, the square root of 2 over 1 times 1 over 3/2. I've just combined 1/2 and 1 there. Times, open brackets again, the square root of 3 over 2 times 2 over 1/2 plus 2 equals 5/2 times square root of 4 over 3 times 3 over 1/2 plus 3 equals 7/2, and so on in our infinite product. Now we're going to do the following thing. We're going to square both sides. I don't really like having square roots in this expression. Square roots can be difficult to work with, so I'm going to square both sides of this equation. But as soon as you do that, if you square a product, you're actually squaring each term in the product. So I'm going to rewrite it that way. I'm going to put that exponent above each term in the product. And then I'm going to carry it out. So each term here gets multiplied by itself. That's all I've done here. And now when we do that multiplication, things get simplified even further. So 1/2 factorial squared. Look at the first term in each of those bracketed groupings. The radical 2 over 1, I'll underline that here, and then the radical 3 over 2. When you multiply those things together, the radicals actually cancel. That's why we squared both sides to begin with. So we get 2 over 1 times 2 over 3. I've just carried out the reciprocal in the second term, times 2 over 3. That's from the next bracketed term, so I'm just grouping them all together. The next one will be 3 over 2, and then 2 divided by 5 over 2 equals 4 over 5, times 4 over 5. And the next one will be 4 over 3, and then 3 over 7 over 2 is 6 over 7, times 6 over 7. And then I haven't written out the terms that follow, but just observing the pattern, we know that the next one should be 5 over 4 times 8 over 9 times 8 over 9, and so on. Okay. So we'll take this a step further. 1/2 factorial squared. I'm now going to multiply the first two terms out of 3 in each of these bracketed groupings. So I'm going to get 4 over 3 times 2 over 3. And then the 2 cancels there, so I'm going to get 6 over 5 times 4 over 5. And then the 3 cancels in the next grouping, so I get 8 over 7 times 6 over 7. And then I get 10 over 9 times 8 over 9. Okay, nice. So I'm going to bring that up to the top line here. And then I'm going to do a very simple rearrangement. I'm just going to flip around each of those terms in the parentheses. So I'm going to get 1/2 factorial squared equals 2/3 times 4/3. I just flip those around, times 4/5 times 6 over 5, times 6 over 7 times 8 over 7, times 8 over 9, times 10 over 9. And now we have a really beautiful pattern emerging here. So I'm going to get rid of these parentheses and we'll be able to see it more clearly. Just filling in the multiplication signs here. This was a known expression involving pi. This is called the Wallace product. It was discovered by Wallace, and he found that pi over 2 equals the infinite product 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times 6 over 5. So what we have here for 1/2 factorial squared is actually very, very close to the Wallace product, which Euler knew and immediately recognized. So I'm going to multiply 2 by 1/2 factorial squared to make this look like the Wallace product. And so that'll be 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times 6 over 5 times 6 over 7 times 8 over 7 times 8 over 9 times 10 over 9, dot, dot, dot. Okay, and remember that equals pi over 2. So we get, I'll put a box around this. And by the way, I'll do another video proving the Wallace product. I don't have the space or time to prove it here. So you'll have to take it from me that that product actually does equal pi over 2, which, by the way, is pretty awesome. But anyway, we get 2 times 1/2 factorial squared equals pi over 2. Again, by the Wallace product definition. Dividing by 2, then we get 1/2 factorial squared equals pi over 4. And finally, we take the square root of both sides. And we find that 1/2 factorial equals the square root of pi over 2. Well, isn't that pretty amazing? Who was expecting that pi would have anything to do with factorials? And yet here it is. 1/2 factorial equals radical pi over 2. So after a result that's staggering, it's probably a good idea to do a sanity check. We're going to check to make sure that the infinite product formula that Euler has put forth really has all the desired properties of the factorial function. So for starters, we know that n factorial equals n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. So if we divide both sides of that equation by n, we get n factorial over n equals n times n minus 1 times n minus 2, times 3 times 2 times 1, all over n. And then, of course, the n in the numerator and the n in the denominator cancel, and we have n factorial over n equals n minus 1 times n minus 2, times 3 times 2 times 1. In other words, that just equals n minus 1 factorial. So we need to check and see if our infinite product definition also has this important property. In other words, we need to prove that n factorial over n, which we know is now n minus 1 factorial, is the same thing as dividing our infinite product formula by n, or equivalently multiplying it by 1 over n. So that's what I'm doing here. I'm just writing out the formula again and multiplying it by 1 over n, and we want to see that that equals n minus 1 factorial. So I'm going to just write that on the top line here on the next board. And to simplify this claim, we're trying to ask, does n minus 1 factorial equal, the limit is m approaches infinity. I'm going to pull that 1 over n into the expression. So multiplying the above expression by 1 over n is the same thing as putting an n in the denominator, times what's already there, n plus 1 times n plus 2, times all the way up to n plus m. And the numerator hasn't changed. I'm just going to fill that in here. And if this infinite product really models the behavior of the factorial function, then we should be able to arrive at that expression through our original definition of the factorial function, plugging in n minus 1 as our exponent. So we should have n minus 1 factorial equals the limit as m approaches infinity of m factorial times m plus 1 to the n minus 1 all over n minus 1 plus 1 times n minus 1 plus 2. I'm just plugging in n minus 1 where we had n before into this infinite product definition, all the way up to n minus 1 plus m. And that expression should reduce to the one that we've written above. So are these expressions equivalent? If they are, then we've proven that our infinite product definition has this important feature of the factorial function. So I've just moved that last line to the top here, and now I'm going to start doing some simplifications. So n minus 1 factorial would then equal the limit as m approaches infinity of m factorial times m plus 1 to the n times m plus 1 to the negative 1. I've just split that exponent. And now I'm going to simplify the terms in the denominator, so that's going to be all over n minus 1 plus 1 is just n. N minus 1 plus 2 is, of course, just n plus 1. And just for increased clarity, we'll write the next few terms, so we have n plus 2 next, all the way up to n minus 1 plus m in the denominator. And now I'm going to multiply this expression by what a former math teacher of mine called a creative form of 1. I'm going to multiply this by n plus m over n plus m. That, of course, is equivalent to multiplying by 1, so I haven't changed the value of this expression in any way. And so we get n minus 1 factorial equals the limit as m approaches infinity. And now I'm going to take that m plus 1 to the minus 1. That's, of course, just 1 over m plus 1. So I'm going to put that m plus 1 in the denominator here. There it is, m plus 1. And that's going to be multiplied by n times n plus 1 times n plus 2 dot 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 times n plus m. So here I've left out the n minus 1 plus m term. It's obviously in there as these numbers are increasing up to n plus m. And then in the numerator we have n plus m as the leading term times m factorial times m plus 1 to the n. And now let's consider what happens in the limit as m approaches infinity. What happens with the first term in the numerator and the denominator? What happens with n plus m over m plus 1? Well, remember that our n is fixed and we're just letting m tend towards infinity. So the limit as m approaches infinity of this expression is the same thing as factoring out an m from the numerator and denominator. If I factor out from the numerator, I get m times n over m plus 1. And in the denominator, I get m times 1 plus 1 over m. And again, our n is fixed. So after I cancel out those m's, I note that n is a fixed value. And so n over m will go to 0 as m goes to infinity, as will 1 over m. And I'm left with 1 over 1, so the ratio approaches 1. So I can cancel out those two terms in the limit as m approaches infinity because their ratio is just 1. And what am I left with? I'm left with n minus 1 factorial equals the limit as m approaches infinity of m factorial times m plus 1 to the n all over n times n plus 1 times n plus 2, and I have to extend this fraction a little bit, dot, 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 times n plus m, which is exactly what we predicted this expression should be equal to for it to be n factorial over n. So we've shown that our infinite product expression has that important property of the factorial function. Furthermore, our infinite product definition of the factorial function has another important attribute. You might recall that we said in our video on Taylor series that 0 factorial is defined as equal to 1. We didn't prove it there, but we're going to prove it now. So why is it? It might seem counterintuitive. And the most basic argument is this. If we were to let n equal 1, then 0 factorial would equal, open parenthesis, 1 minus 1 factorial. So now, looking at this expression, we have an n minus 1 factorial expression here, where we're letting n equal to 1. N minus 1 factorial is just n factorial over n, so this would be 1 factorial over 1. And I'll just highlight that again in red here. Remember that n minus 1 factorial equals n factorial over n. Well, 1 factorial is just 1, so 1 over 1, that's just 1. So, does that fact that 0 factorial is defined as being equal to 1, does that hold true in our infinite product definition of the factorial function? If it does, then we should be reasonably convinced that what we're dealing with really does fully model all the attributes of the factorial. Well, let's look at this. We've already shown here in this video that n minus 1 factorial equals the limit as m approaches infinity of the expression m factorial times m plus 1 to the n, all over n times n plus 1 times n plus 2 all the way up to n plus m. So now let's let n equal 1. Then we'll be able to compute 0 factorial. So 0 factorial then would equal the limit as m approaches infinity of the expression m factorial times m plus 1 to the 1 over, letting n equal 1, over 1 times 1 plus 1, and we sure hope times 1 plus 2 all the way up to 1 plus m, and we sure hope that this expression reduces to 1. Well, let's see that it does. Well, looking at the numerator here, m plus 1 times m factorial, I'm just writing that out again, 0 factorial equals this limit as m approaches infinity. M plus 1 times m factorial is m plus 1 factorial. And if you look at the denominator, 1 times 2 times 3 all the way up to m plus 1, that's also m plus 1 factorial. It cancels and equals 1. Excellent. So now I'm going to introduce some new terminology. I'm going to start talking about something called the gamma function. The gamma function is really just the n minus 1 factorial function. But for historical reasons, it gets its own special Greek letter gamma. And we write, or rather we define, gamma of n equals n minus 1 factorial, or using the infinite product definition that we've established, the limit as m approaches infinity of the expression m factorial times m plus 1 to the n all over n times n plus 1 times n plus 2. This expression is identical to the infinite product for the factorial function, except that it also has an n in the denominator. And I'm going to put a box around that because that's an important infinite product definition. Again, this is really the heart of this video. This is the infinite product definition of the gamma function. So there's a modification of this infinite product formula attributed to Gauss, and I'm going to derive it here by making the following variable substitution. We're going to let p equal m plus 1 in this expression. Then p minus 1 will equal m, and we say gamma of n, which we know equals n minus 1 factorial, would then be the limit not as m approaches infinity, but as p approaches infinity. For the expression, again, p minus 1 equals m, so p minus 1 factorial times p to the n all over n times n plus 1 times n plus 2 all the way up to n plus p minus 1. That's being substituted in for m here. And now I'm going to multiply that by p over n plus p. Note that in the limit, as p goes to infinity, p over n plus p just equals 1 for a fixed value of n. So we end up getting here gamma of n equals n minus 1 factorial, which equals the limit as p approaches infinity of p times p minus 1 factorial is just p factorial times p to the n over n times n plus 1 all the way up to n plus p. And that's a very quick derivation of the Gauss version of the infinite product formula of the gamma function. I'm just putting that there so if you see it in the literature, it doesn't confuse you. I now want to talk about some special values of the gamma function. Specifically, we have already found that 1/2 factorial equals the square root of pi over 2. But we know that gamma of n is defined as n minus 1 factorial, which is again n factorial over n. Therefore, we can write gamma of 1/2 equals 1/2 factorial over 1/2, which equals radical pi over 2 over 1/2. So the 2's cancel there in both denominators, and we get gamma of 1/2 equals radical pi. Neat. Another consequence of our definition of the gamma function is as follows. We have gamma of n equals n minus 1 factorial, but we just showed gamma of 1/2 equals the square root of pi. Therefore, we would write gamma of 1/2 equals 1/2 minus 1, close parentheses, factorial, or negative 1/2 factorial. In other words, we've just extended the definition of factorials to include negative fractions. Again, factorials are now defined for negative fractions. So that's pretty cool. So let's see how this works. Again, we already know that gamma of n is defined as n minus 1 factorial, which is equal to n factorial over n. And we just established that gamma of 1/2 is the square root of pi, which is equal to negative 1/2 factorial. So we can continue this process and find negative 3/2 factorial. How would we do that? Well, remember this formula here, n minus 1 factorial equals n factorial over n. Negative 3/2 equals negative 1/2 minus 1. So negative 3/2 factorial would equal negative 1/2 factorial over negative 1/2, which would be negative 2 times the square root of pi. How about the next one? Negative 5/2 equals negative 3/2 minus 1. So negative 5/2 factorial would equal negative 3/2 factorial over negative 3/2. Well, that will just be equal to negative 2 times the square root of pi over negative 3/2. And that equals 4/3 times the square root of pi. We can also apply this reasoning and work in the other direction. Since we know n minus 1 factorial equals gamma of n, which equals n factorial over n, then n times gamma of n must equal n factorial. Knowing that gamma of 1/2 equals radical pi would then imply that 1/2 times gamma of 1/2 equals 1/2 times the square root of pi, which equals 1/2 factorial. Well, we knew that already, but we can keep going. For example, to find 3/2 factorial. 3/2 times gamma of 3/2, that would be 3/2 factorial, equals 3/2 times gamma of 3/2, which equals 1/2 factorial. So that's 3/2 times 1/2 radical pi. So we now found that 3/2 factorial equals 3/4 times the square root of pi. To find 5/2 factorial, well, that would just be 5/2 times gamma of 5/2, which is 5/2 times 3/2 factorial, which we just determined. So that would be 5/2 times 3/4 the square root of pi. And that equals 15 over 8 times the square root of pi, etc. So using these recursive definitions, we can find the values of the factorial function for any fraction. If I know 1/2 factorial, I know the factorial for any number that could be written as 1/2 plus or minus n, where n is an integer. But note that this process does not work for finding the factorials of negative integers. In fact, the factorial function isn't going to be defined on negative integers. Consider, what would gamma of 0 equal? Well, we already know n minus 1 factorial equals n factorial over n. I don't want to belabor that point, but look what happens if we were to try to find gamma of 0. That would be negative 1 factorial, which would be 0 factorial over 0. Well, here we have a problem that becomes 1 over 0, and we can't divide by 0. We say here that that expression is undefined, or in calculus terms, that the limit does not exist. And this isn't only the case for -1 factorial. Factorial of all negative integers are undefined. Consider, for example, gamma of -2. By our definition, this is our infinite product definition, gamma of -2 would be the limit as m approaches infinity of m factorial times m plus 1 to the -2 all over -2 times -2 plus 1, which I'm writing here, times -2 plus 2, I hope you guys are seeing the problem here, times -2 plus m. So this -2 plus 2 term equals 0, and we then have a 0 in the product of our denominator. So again, this whole expression will be undefined, or we would say the limit doesn't exist. And in fact, if we plug in any negative integer into this infinite product formula for the gamma function or the factorial function, we end up with a 0 in the denominator. So our infinite product definition of the factorial function and gamma function has extended the value of factorial to fractions, but at negative integer values, the factorial function is undefined. So this is what the gamma function looks like if you graph the whole thing. And the middle dashed line is actually the y-axis, which is here a vertical asymptote. Now this is the gamma function, so the graph is going to be right shifted by 1 relative to the factorial function. And over here you can see the factorials of the positive integers, or rather the gamma function of the positive integers, very rapidly increasing. You can see here gamma of 2 is equal to 1, and then the curve dips down, gamma of 1/2 equals radical pi, and then it comes back up, gamma of 1 also equals 1, and these are the values the gamma function takes in the negative fractions, with a vertical asymptote for every negative integer. Well, I hope you enjoyed this introduction to the gamma function. Next time we're going to derive an alternative definition of the gamma function, which might be more familiar to many of you. We're going to derive the integral expression for the gamma function, and I'll show you how Euler came up with that. So thank you so much for watching. I look forward to seeing you all next time.